Hi everyone. Today we will be doing a demo for the topic of Bernoulli equation. If you remember from Bernoulli principle, we had a balance between pressure, kinetic energy and potential energy. If potential energy of fluid elements doesn't change that much, pressure and kinetic energy summed together per unit volume should be constant. This means that when we have an increase in velocity due to acceleration of fluid elements, we should have a decrease in pressure and vice versa. So points with higher local velocity will have lower pressure and points with lower local velocity will have higher pressure. P plus half of rho v squared remains constant. This demo will demonstrate a nice consequence of this. What I have is a hair dryer that blows the air vertically downward through a funnel that is attached to the hair dryer using some elastics cut from a balloon. As you can see, if I turn it down and the flow is acting downward and gravity also is acting downward, if I put a ping pong ball in this flow, what I expect is the fact that the ping pong ball will probably be thrown downward. Let's try it and see what we observe. This is at low velocity, and then I can go to high velocities. You can clearly see that despite both acting downward, the ping pong ball actually remains suspended or levitated in air. It's not falling down and it's suspended in air. Now if I turn the velocity off, I can clearly see that in the absence of the jet, the ping pong ball actually indeed follows the gravity and it falls down. So it's something really interesting about this interaction that counterintuitively, by blowing air towards an object and gravity also acting downward, both the jet and gravity acting downward, something generates enough force or lift on this object, on this ping pong ball, to keep it levitated or suspended in the air. Let's look at a simple drawing of this problem and let's think what's really the fundamental mechanism here. If my ping pong ball inside this funnel is drawn in this geometry, as the flow comes from the narrow channel of the funnel, it hits this contraction that is made by the geometry of the ping pong ball, and it has to go through even a smaller and thinner gap or contraction. Remember, as the gap becomes smaller, conservation of mass tells us that to conserve mass, velocity has to increase. Velocity increases, and then as it gets into a larger area, again decreases back to its previous values. But the fact that in this thin gap velocity has become large tells us that we develop certainly a decrease in pressure. Bernoulli tells us P plus half rho v squared should remain constant. So if velocity increases, pressure has to decrease. Indeed, we generate some suction pressure in these areas and some higher pressure in the other parts. The resulting net force consequently will be upward. You have suction on top and a higher pressure at the bottom of the ping pong. The resulting net force will be upward, and that can be large enough that will win over gravity. So if I draw the weight of the object going downward, you can imagine that, so if the W is downward, you can imagine that these aerodynamic forces will give you a lift that probably is large enough to sustain the weight of the object. That is the main reason why we see this counterintuitive result when we do this demo. You can easily try this demo at home. All you need is to buy a funnel and connect it to your hair dryer with some cut elastics of party balloons. I hope you try it at home, and I hope you enjoy it. In this other demo that we will do today, we like to look at the other principle that we learned through Euler equations. If you remember, Euler equations could be written both parallel or normal to streamlines. The consequence of writing Euler equation normal to streamlines was the idea that if streamlines are getting curved, as we move away from center of curvature, pressure has to increase. That was a physical mechanism to sustain the centripetal acceleration that we developed by sending fluid elements around curved geometries or trajectories. What we have here is a certain demo that will show you a consequence of this principle. Again, what you need is a simple hair dryer. And if I turn it on right now, it will flow the air from this side upward. So I'm pushing the jet upward. And what I want to do is to throw a ping pong ball in the trajectory of this jet and see what's about to happen. So clearly you can see that the ping pong ball stays in the jet and it stays levitated. This is not surprising. There's a momentum of the jet. It hits the ball, and that momentum will lead to a big enough, large enough force to counterbalance the weight of the ping pong ball. If I move the hairdryer to the left or to the right, as the jet is moving, the ping pong ball remains almost like a connected ghost attached to the hairdryer through the jet of air, and it moves to the left or right. This is slightly more complex to think of, but maybe the best way to show something counterintuitive is when I start to tilt the flow. So I am tilting the flow of the hairdryer, and I hope you can see that as I start tilting it, there is a certain angle where the jet is not anymore vertical. The jet has a certain oblique angle, but still the ping pong ball can keep its position upward. So let's try one more time. Oops. So right now it's vertical, and as I tilt it, hopefully you see that there's a certain angle that the jet can still hold the object vertical, despite the fact that it's hitting the object or the ping pong in a tilted manner. But if I exceed that angle, you see that ping pong ball falls down. This idea that the ping pong ball can indeed remain levitated or suspended in air, even with a tilted jet, not a vertical jet, requires a little bit of thinking. Let's go through that together. Somebody may say, oh, that's just a consequence of the drag force. If you are hitting an object with a certain angle, you develop a certain drag force, and that drag force probably will be very much parallel to the velocity that you hit. So there is a drag force that is parallel to your velocity, and the vertical component of that is enough to be in equilibrium with the weight of the ping pong ball. Problem solved. But if you think about it, that doesn't make really that much sense. Because if the drag force has a vertical component enough to balance weight, what will happen to its horizontal force? Nothing to balance it there. So the ping pong ball not only will feel that it should vertically not move, it will also feel an unbalanced force that goes in this direction horizontally, and it will start shifting or drifting horizontally. But we saw that that didn't happen. So we clearly see that there is a missing force here in our balance. That missing force comes from an effect that people call quanta effect. When an object is like a curved object like this is hit by a velocity in an oblique angle, what usually happens, the flow loses its symmetry and you get slightly more curved streamlines here and slightly larger portion of the flow going around the object that way than this side. So your jet coming from far away will form some local streamlines around the object that look like that. This breakage of symmetry and higher curved nature of streamlines on this side will guarantee that your pressure here will be much smaller than the ambient pressure outside, which I call P sub A, compared to the pressure down here. And you clearly see that on one side you have higher pressure, on the other side you have lower pressure, pressure side here and suction side on the other side. So overall you generate what people call a lift force. And this lift force, which is a consequence of Euler equation normal to the streamlines and the fact that the streamlines are getting more curved on one side because of this breakage of symmetry, will be the component that we needed. Now with the lift force and the drag force and the weight, everything is in the balance. The summation of the vertical components of lift and drag will be in balance with the weight, and the horizontal ones of drag and lift will be cancelling each other. That's why a ping pong ball can indeed be in equilibrium, even though we hit the ping pong ball with a tilted jet.